Hello, my name is Chelsea Scott, and welcome to this OpenTopography video. In this video, I'm going to talk about why you might have found these weird triangles in a digital elevation model, DEM, or a digital terrain model, DTM. And so here we're looking at a topographic hillshade of an area in South Carolina. And if you zoom out, it looks fine. You see this stream that curves around in this particular area. But if you zoom in, particularly to the stream, you see these weird triangles that cross the stream, either completely across or halfway, and they're essentially located along the whole length of the stream. And so these triangles reflect errors in the gridding approach, and specifically while applying the Triangulated Irregular Network, or TIN, algorithm. So in this video, I'm going to discuss what these errors are in a little bit more detail, and then show you some approaches that you can experiment with to get rid of these errors, or at least make them less bad. So here we are zoomed in, looking at that same area from before. And using the red arrows, I've highlighted some of these tinning errors. And so these are these triangular shaped features that you see especially in hillshades, slopeshades, or topographic differencing results. So essentially products that are looking at, for hillshades or slopeshades, fairly subtle changes in the shape of the landscape or differencing, then you might see these because they're going to be recorded differently. You'll have different tin errors between the two different data sets that go into differencing. And these errors largely originate because there's not enough points to construct a digital terrain model or DEM, digital elevation model, at the desired resolution. And they're particularly common in riparian zones, so along streams, where there are very few ground returns due to the water and high vegetation. And these are annoying to look at in a slope shade or hill shade, but they are really problematic for doing hydro routing. So here we have in white, this is looking at a stream network. And what's actually interesting here is that this area, there's a break in the stream, so essentially have two largely separated streams in this area, whereas ideally we would have one larger stream that would go through and cross the DTM, essentially as you can see with the arrow. But that's not what we see here. Here we see these two streams divided into this part of the data set and then this part of the data set. And let's look a little bit more at the data to understand the origin of these errors. So here we're looking at the 3D point cloud shown in Poetry. In both cases, they're colored by elevation. The left shows the full point cloud colored by elevation. And these bumpy features we see on the top, those represent the vegetation. So we can see overall there's a lot of vegetation consistent with the weather in the southeastern portion of the US. But we do see this stream area, which is associated with a little bit thinner vegetation. This here is the 3D point cloud, but just of the ground points. And what's interesting is that along often the center, sometimes the edges of the stream, we don't see any returned ground points. So this means that we're very likely to have holes in a digital terrain model because we just don't have any information of where we're really seeing the bare earth in that area. All right, and this slide here is to emphasize really the lack of ground returns in some areas over especially a riparian zone. So in this plot, I've colored by number of points per square meter of ground classified points. And the blue represents essentially 0 returned ground points in that square meter. And then the red, or pink to red, indicates increasingly higher density of ground classified points. And in particular, you'll see along the stream here, we have a lot of blue. And so we really have a lot of area where there are no ground return points, and that makes constructing a DTM quite challenging. And so recall for making a 1 meter digital terrain model, we really need at least and ideally more than 1 point per square meter of ground classified points. And so here where we see those blue, which are 0 points per square meter, really we don't have enough points. And so this is going to include areas where we have the streams, or the stream, the lake, and then other areas with dense vegetation. All right, so what can we do? Well, there's a few different options that we can look at. First is to better classify ground points. Sometimes the ground points can often be quite misclassified. And in particular, if ground points have points that actually are on the ground are represented or labeled as unclassified, that can lead to problems. And so an option is to reclassify, which may increase the number of ground classified points. Second is to decrease the edge length while applying the tinning algorithm, and I'll show you that. You can look at different local interpolation methods, for example, nearest neighbor or local minima. You could add stream center lines as break lines. For example, you can do this in LAS tools. But to do this, you do need the stream elevation. And finally, you can hydrologically condition a DEM or the DTM. So this is to fill pits, level water bodies, and or force downstream gradients of the stream. All right, so we're going to look at a few of these. All right, so the first is to decrease edge length. So in OpenTopography, if you make a DTM using the tinning algorithm, our default triangle size used in the tinning algorithm is 50 meters. But you can change this. So if you go to the DEM generation, then here you'll see the option for the maximum triangle size. And our default is 50 meters, but you can change that to 10, for example. And here are the results. So in this case, it looks like at first glance, the results maybe look a little bit better. The triangles aren't, at least to me, they don't stand out quite so much. However, they are still there, and some of them have been replaced with no data. So this is maybe a little bit better. Another approach that you can use is local minima gridding. And in this case, the gridding algorithms performs a search over a predefined radius to find the local minima and then assigns that to the pixel value. And so here is a plot showing the local minima for DTM at a 1 meter resolution using a 1.4 meter search radius. Here the triangles are gone, which is good news. However, we do see quite a bit of these white no data areas, both along the stream and then here along the adjacent hills, where there is still quite dense vegetation. And this here is also a 1 meter DTM, but it's made with a larger, so a 2.8 meter search radius. And here we do see fewer no data areas in the river and none on the hill slopes. So in that way, it does look better. This product is, however, at a lower resolution than the one above. So you have to decide for your project if that essentially lower resolution with the bigger search radius is more useful to you. And OpenTopography has hydrologic terrain analysis tools located within the processing workflow. So you can apply them, for example, to check the box to get a hydrologically conditioned DEM, which is shown here. So in this case, just using the quite simple default options really doesn't give us much an improvement, as we still see these triangles throughout. So in summary here, this option of using The local minima is what got us our best results at decreasing these triangles from the TAN algorithm. If you're looking to invest more time in correcting these errors, I do invite you to look at again, exploring the options within hydrologic conditioning of a DEM or DTM, as you can get better results than shown here, and or adding a center line for the stream to predefine that elevation and downflow gradient. And that concludes this video. Thank you for watching.